Hello everyone, and welcome to the solutions video lesson. So solutions are mixtures that are homogeneous. In other words, the components of this mixture are dissolved into each other. And we have two components. We have what's known as the solvent. This is our material present in greatest amounts. In our example here, that would be the water. And our solute or solutes, which are present in lesser amount, and that would in this case be the salt. So we could say that our salt, the solute, is dissolving into the water, the solvent. Now we tend to think about solutions as being liquid, like in the example shown there, but they can actually be any different state. We have gaseous solutions which contain, which air is a fantastic example of, where oxygen is dissolved into nitrogen, but we have other solutes as well. We have water vapor, methane, argon, carbon dioxide, things like that as well. And of course, we're familiar with liquid solutions. We can have gases dissolved in water, like an example of carbonated water or household ammonia. We can have liquids dissolved into liquids. Vinegar is a great example of this, where acetic acid is dissolved into water. Or liquor would also be an example, where we have ethanol dissolved into water. We can have solids dissolved into liquids, like salt water or sugar water, but our solvent doesn't need to be water. So an example of tincture of iodine, we've dissolved iodine into ethanol. And then finally we can have solid solutions, and these are where we have solids dissolved into solids. And metal alloys are fantastic examples of this. So carbon dissolved into iron is what's known as steel, but it's an example of a solid solution. So please pause your video and complete question number 1. Welcome back everyone. Let's talk a little bit more about solutions. So when we take something ionic and we dissolve it to water, a process called dissociation occurs. And so our ionic compound, when it's a solid, we have these ions densely packed together, and the cations and anions are attracted to each other because of their opposite charges. Water molecules, however, have charges of their own, and they're able to come in and actually pluck ions out of this crystal. So right here we have sodium ions. They've been plucked out of the crystal by water molecules. And notice that the negative or the oxygen end of the water molecule is attracted to the sodium ion. And the reason for this is that the oxygen end has the lone pairs. It's more electronegative, so it's rich in electrons. And this, of course, means the hydrogen end must be kind of positive in charge, and that's going to be attracted to anions, like in this example, the chloride ion. So any compound that forms ions when dissolved in water is what's known as an electrolyte. And we have strong electrolytes. These are compounds that completely dissolve. Ionic compounds that are soluble in water, as well as strong acids and strong bases, are all examples of these. Weak electrolytes are compounds that produce some ions when they dissolve in solution, but not as many as strong electrolytes. These are typically weak acids or weak bases. And then finally we have non-electrolytes, which are going to be molecules, or in other words covalent compounds, that don't produce ions when dissolved in water. And really common examples of these would be things that are like carbohydrates, like starches and sugars, as well as alcohols. And there's a very simple way to test what type of electrolyte we have, and that has to do with conductivity. In order for water to conduct electricity, we need to have ions present, and the more ions, the more conductive the water. So strong electrolytes conduct a lot of electricity, so we could just use a simple test where we try and conduct electricity across water using a light bulb and some sort of power supply. And a weak electrolyte is going to be less conductive because there's fewer ions in that solution. And then finally, a non-electrolyte will see no illumination because little to no electricity is able to pass through the water without the presence of those ions. So this is something that tends to trip students up a little bit. When we have ionic compounds and they dissolve in water, they're going to break down into ions. But what does that really look like? So if we took calcium chloride, for instance, it's going to separate into the individual ions. So we'd have our calcium ions in solution, as well as our two chloride ions. And notice these don't stay together as a Cl2 unit. The reason for that is the chloride ions are negatively charged and they're going to repel each other. When we have polyatomic ions in play, however, things go a little differently. The polyatomic ions generally stay together as one unit. So what we're going to see here is our phosphate's going to stay phosphate, but our potassiums, that's not a polyatomic ion, so that's going to dissociate. And so what we'd see here is we'd have all three of our potassiums in solution, but our phosphate would stay as one unit. And so our answers here would be C and A. I'd like you to now pause the video and please complete question number 2 in the activity. Welcome back, everyone. We are now going to talk about concentration. So concentration comes in various forms, but they're all pretty much a measure of how much solute we have present in a given amount of solution. And so we'll start out with percent concentration. We have what's known as mass percent, which is pretty much what the name implies. It's going to be our mass of our solute over our total mass of solution, which is mass of solute plus mass of solvent. So suppose we have a solution that has 8 grams of KCl dissolved into 42 grams of water. Our mass percent here would be our 8 grams of solute, the KCl in this case. And the authors made a little typo here. That should be a lowercase l, but let's not worry about that. And then over our mass of solution, which is going to be our 8 grams of solute plus our 42 grams of solvent. And we do all our math here, multiply by 100, we end up with 16.0 mass percent. We also have what's known as volume percent. And this is calculated in a very similar way, except it's going to be volume of solute over volume of solution. We have the example here. We have a bottle that contains 59 milliliters of lemon extract, and 49 milliliters of that extract are composed of alcohol. What is the volume percent of alcohol in the solution? So our volume of solute over our total volume of solution times 100 gives us 83% volume of alcohol. Molarity is a slightly different but highly useful measure of concentration. It's going to measure moles of solute over liters of solution. And so a 2 molar solution, you might have seen these uppercase M's. This uppercase M represents molarity. A 2 molar solution of NaCl is going to contain 2 moles of NaCl in every liter of solution. And so one thing to be careful of here is that moles and molarity are different things. So molarity is a measure of concentration. It's moles over liters. And moles is a measure of a number of particles. So they're related to each other, but again, moles and molarity are actually 2 separate things. So we're asked the question, what is the molarity of a 0.350 liter solution that contains 46 grams of KCl? Well, in order to find molarity, we need 2 things. We need our moles and our liters. Our liters are given, so that's easy enough. We have to find our moles now. So we're going to use our molar mass of potassium chloride in conjunction with our 46 grams. Set up our unit cancellation there. That's the sound of unit cancellation. There we go. 0.62 moles of KCl. Now setting up our molarity, moles over liters means this is a 1.8 molar solution, or 1.8 moles per liter solution of KCl. Here we have a slightly different problem. How many liters of 2 molar NaCl solution are needed to provide 67.3 grams of NaCl? So here's our 67.3 grams of NaCl. We're going to convert that into moles using our molar mass, unit cancellation, and then we're going to go from moles to liters using our molarity. So we'll frequently use molarity as a conversion factor, and that's actually going to come up later in this video. So please pause the video and now complete questions 3 and 4. Welcome back, everyone. Let's talk about dilution. So dilution is actually a process that you're familiar with. So if we take 1 can of our orange juice concentrate and dump it into our pitcher right here, and then we're going to add some water to it, we're adding more solvent, we're going to decrease the concentration right here through this process of dilution. And so we have a handy dandy equation we use in chemistry for these types of calculations. It states that C1 times V1 equals C2 times V2. You can probably guess that C1 is concentration 1, our initial concentration, V1 is our initial volume, C2 is our final concentration, V2 is our final volume. So I have bad news, we might have to do some algebraic rearrangement here. If you're soft and fuzzy on that, make sure you brush up on it because it's going to come up a few times this quarter. And any of the math tutors will be happy to help you with that. And so just some clarifications here about units. We can use any units of concentration we want so long as C1 and C2 have the same units. We can use any units of volume that we want so long as the volume's in the same units. So they can both be milliliters, they can both be liters or gallons or whatever so long as they're the same units. What volume of a 2% HCl solution can be prepared by diluting 25.0 milliliters of a 14.0 HCl solution. So our initial concentration is going to be 14%. Our initial volume is going to be 25.0 milliliters, and our final concentration is going to be 2.00 milliliters. So here we've rearranged the equation to solve for V2. We've divided both sides by C2 and flipped around the equation to end up with this quantity right here. Now we're going to plug in our values here. So volume 1 was our 25.0 milliliters. Concentration 1 is our 14% right here. And then concentration 2 is our 2% right here. And so crunching our numbers, we're going to end up with 175 milliliters. Please pause the video and complete question number 5 in the activity. Welcome back, everyone. I have some great news. We're almost done here. We just have one last topic to talk about, and that's going to be solution stoichiometry. So here we have a stoichiometry diagram. And previously, in Chapter 6, we talked about the fact that we can go from grams of a compound into moles of that compound using the molar mass. We can go from moles of one compound into moles of another compound using our balanced chemical equation. And then finally, we can go from moles of one compound into compound B into grams of compound B, again using our molar mass. Now, we can sort of add on to this sort of scheme right here. We can also go from volume of solution into moles of solute using our molarity. Or we can go from moles of solute into liters of solution, again using our molarity. So we'll be able to do all the sorts of molarity problems we talked about before, things like limiting reactant problems, percent yield if I'm feeling really mean on an exam, but let's just start with something pretty simple here. How many liters of 3.00 molar HCl are needed to completely react with 4.85 grams of calcium carbonate? So in case you're wondering, HCl is stomach acid, calcium carbonate is the active ingredient in Tums, so this is the same reaction that's used in order to neutralize stomach acid when you take the medication Tums. So here's our balanced chemical equation. On the exam, of course, I'd be mean and make you balance your own equations, but we're given a balanced one right here. And so we're going to start out with our 4.85 grams of calcium carbonate. So we're going to start out just like we've talked about before. We're going to use our molar mass to convert that into moles of calcium carbonate. And then we're going to use our balanced equation, so everything just like we did in Chapter 6, but now we're going to diverge a little bit. So now we're going to use our molarity to go from moles of HCl into liters of HCl right here. So we set this up like a conversion factor so it cancels out our moles, and we're going to end up with 0.0323 liters. Or if you're asked to figure out milliliters, you'd simply simply multiply that by 1,000, so you'd have 32.3 milliliters of HCl. So I want to point out the difference here is that for our stoichiometry calculations, if we're dealing with solutions, sometimes we'll use molarities rather than molar masses. But we still have the same moles to moles comparison from our balanced equation we had before in any sort of molarity problem, in any sort of stoichiometry problem. So please pause the video and complete question number 6. Once you finish that, shoot on over to discussion and talk to your teammates over there. See how things are going, help each other out, get those easy points.